Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the conference. G-SDDP and G-DDP. Generalized Dual Dynamic Programming. Applications in the electric sector. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. Most think that an expert in operations research is a magician who does not understand nor explain anything. Others think that he is a scientist who is impossible to understand. Very few understand that he is a professional expert in solving real-world problems using mathematical models. Generalized Dual Dynamic Programming. G-DDP. The structure of Generalized Dual Dynamic Programming, G-SDDP and G-DDP, follows that of dynamic programming, dividing the variables into state and control. The diagram presents the standard Benders partition and decomposition. Three types of cuts can be considered. SBC, standard Benders cuts, corresponds to the methodology proposed by Benders that solves a single subproblem that integrates the subproblems for all the dimensions of decomposition and generates only one cut in each iteration. DBC, decoupled Benders cuts, corresponds to a variation of BT, which solves in each iteration a subproblem for each dimension of decomposition, and generates a decoupled cut, that are coupled in the objective function. UBC, unified Benders cuts, when the mathematical conditions are met, it corresponds to a variation of BT, that solves in each iteration a subset of all subproblems. Solving only one subproblem, UBC generates decoupled cuts for each decomposition dimension, periods and/or random scenarios. The cuts are coupled in the coordinator. The image shows the computer used for experiments. The codes of the experiments carried out. Full, integrate or monolithic model. G-DDP-UBC, unified cuts, integrated coordinator. These experiments are performed in order according to the following criteria: period, total demand, and alternation. G-DDP-SDC, decoupled cuts, integrated coordinator. DDP, dual dynamic programming, version GAMS, and G-DDP-SDDP, decoupled cuts, DDP coordinator. Three sequences are considered for the order of unified cuts, by periods, TEM, alternating, ALT, and according to the magnitude of aggregate demand, DEM. The table presents the results of the experiments, for a linear dispatch model. The complexity of the case does not justify large-scale methodologies, but they are useful for comparing large-scale methodologies and demonstrating their convergence. G-DDP with UBC is faster than any other large-scale Benders methodology, regardless of the order of selection of the subproblem. G-DDP with UBC is faster than G-DDP with DBC. G-DDP with UBC is 8 times faster than DDP, and with DBC 4.5 times faster. G-DDP with integrate coordinator is 22.79 times faster than G-DDP with DDP coordinator. Conclusion: G-DDP is faster than DDP. The diagram presents the convergence of the experiments, G-DDP-SDC. Deterministic economic dispatch of electric systems. Linear model. The article. Mixed nonlinear economic dispatch using G-SDDP with unified Benders cuts. Presents detailed information about this case. The paper. Test cases for unit commitment and hydrothermal scheduling problems. Published by IEEE are taken as a reference. The process involves conducting experiments in which the reference conditions are modified. The first experiment is economic dispatch of electrical systems. Linear model. The linear model refers to the cost of the thermal operation, which is considered linear. Hydroplants, configuration. Original data: 12 hydroplants, 8 reservoirs, 6 thermal plants, 1 deficit plant, and 24-hour planning horizon. The tables present the parameters of the original IEEE case. The G-DDP formulation of the case is State variables. ATI hydro unit outflow, QHTI hydro unit power generation, GHT total hydraulic generation, VTI reservoir operating volumen, QTI turbine outflow, and SBTI spillage outflow. Control variables. GTTJ thermal generation. The table presents the structure of the G-DDP, composed of two problems, the coordinator and the subproblem. To use the standard Benders method, the following structure has been created. The coordinating model is based on the control of the discrete and nonlinear part, in this case those associated with thermoelectric power plants. The subproblem is related to the linear part of the model. The G-DDP subproblem formulation is: state variables. QQHTI turbinated outflow. What TI water balance? GQTTI hydraulic generation. GUT-T total hydraulic generation, and MGHT maximum hydraulic generation. Constraints. QQHT, I turbinated outflow. What TI water balance? GQTT, I hydraulic generation. GUT-T total hydraulic generation, and MGHT maximum hydraulic generation. The formulation of the G-DDP control is: control variables. GTTJ thermal generation. Constraints. GUT-TI total hydraulic generation, and ELDT, electricity demand. The image presents the fundamental elements of the problem, indexes, sets, and parameters. The image presents the variables and constraints of the problem. Deterministic economic dispatch of electric systems. Mixed linear model. Modified data. 12 hydro plants, 8 reservoirs, 6 thermal plants, start, stop, 1 deficit plant, and 24-hour planning horizon. The G-DDP formulation of the case is the same as the linear one but incorporates new control variables. GTT, G thermal generation SRT, J start thermal plant STT, J state thermal plant, off, on. The mixed linear model refers to the cost of thermal operation, which considers the costs of starting and shutting down. To model it, binary variables are required. Data were taken from IEEE. The table presents the structure of the G-DDP, composed of two problems, the coordinator and the subproblem. Variables related to the startup and shutdown of thermal turbines are new control variables. The image presents the fundamental elements of the problem, indexes, sets, and parameters. The image presents the variables and constraints of the problem, in blue the new elements of the mixed linear model. The start-stop equations of a must-run plant are presented. Costs are associated with plant startup, variable SRTJ. The binary variable SDT, J indicates on if it is equal to 1 and off otherwise. The table summarizes the formulation of the linear mixed model. Experiments were carried out with a monolithic model, full space, with decoupled DBC, and with unified UBC, cuts. The maximum processing time was 1000 seconds. In 2 cases, the full space algorithm failed to achieve the solution. UBC cuts were always faster than DBC cuts. The graphs show the average time based on the number of periods. G-SDDP. Stochastic Economic Dispatch of Electric Systems. The article. Mixed nonlinear economic dispatch using G-SDDP with unified Benders cuts. Presents detailed information about this case. G-SDDP, parallel stochastic optimization without anticipative constraints. The complexity of the case does not justify large-scale methodologies, but it is useful to compare them and demonstrate their convergence. The graph shows the average solution time versus the time stages for the full space and DBC. The graph shows the relationship between G-DDP performance ratio and full space. GAM speed depends on solver connection options. For serial symmetrical problems it is recommended to use GUS. The experiments show that G-SDDP is approximately 100 times faster than SDDP. Experiments show that G-SDDP is 3.28 times faster with 20 scenarios, 9.63 with 50 scenarios, and with 100 scenarios full pace cannot solve the case. The graph presents the cumulative time for stochastic linear economic dispatch using unified cuts and inexact solutions. The graph presents the average time by scenario, which decreases with the scenarios. The unit commitment of electric systems mixed nonlinear model includes a pumping station in the water resources system. In the reservoir 12 there is a pumping station that allows the water to rise. The model performs the operation. IEEE data is used. Data extracted from IEEE. The image presents the fundamental elements of the problem, indexes, sets, and parameters. The image presents the variables and constraints of the problem. In blue, the new elements of the pumping model. The G-DDP formulation is the same as the linear one but incorporates new state variables. PU-TIP water pumped PWTI power used in pumping station BPTI binary control pumping. The table presents the structure of the G-DDP. The new algebraic elements, associated with the pumping station, are part of the subproblem. The image presents the fundamental elements of the problem, indexes, sets, and parameters. Variables are also included. The formulations of the elements of the pumping system are presented. Two cases were executed, one with a nonlinear model and the other with a mixed nonlinear model. The results show the efficiency of the complex solver. The periods indicate the hours of operation of the daily unit commitment. The graph presents the average time by scenario for the nonlinear mixed model, which decreases with the scenarios. The graph presents the cumulative time by scenario. Optimal expansion of electric systems, including scientific risk analysis. The article, G-SDDP and Risk Management, Theory and Supply Chain Design, presents detailed information about this case. The case corresponds to the stochastic optimization of the expansion, in parallel, of the hydraulic system, composed of 4 hydraulic power plants. The tables present the parameters, and the graph the topology, of the new system. The graph shows the growth in demand for the current system. The new data are 12 hydro plants plus 4 expansions, 8 reservoirs plus 2 expansions, 6 thermal plants plus 3 expansions, 1 deficit plant, and 24-hour planning horizon. Like a typical day for 25 years. The value at risk, VAR, is associated with a mathematically defined level of probability, by which the probability of it being exceeded is equal to a reference parametric probability. The conditional value at risk, CAR, also known as mean excess loss, is defined as the expected cost conditioned in that the cost exceeds the value at risk, VAR. Risk arises in the probability concentration and a tail of the probability distribution function. If the risk comes from a high cost, it is reflected in exceeding a high limit of probability. If it comes from low income, the risk arises from not exceeding a low probability. CAR is commonly used in stochastic optimization models when the goal is to minimize or limit VAR. In this case, empirical distributions are included for risk control through the value at risk and the conditional value at risk. The graph presents the empirical distribution obtained using G-SDDP without risk management. It corresponds to the conventional expansion model, which produces the riskiest distribution of income, because the range covered by the empirical solution is the largest. The number of scenarios determines the fit of the empirical distribution function resulting from stochastic optimization models. Therefore, the power of the computer becomes an important parameter. G-SDDP accepts the criterion of statistical convergence, based on the accuracy of the estimator with respect to the value of the objective function, or another random variable of the model. The standard error estimator, C, is calculated during execution, and its calculation is used to determine convergence. Risk management aims to control the extremes of the probability distribution function, since exceeding them or not exceeding them generates risk. For example, if the top end is reduced to the red line, there will be less risk of high costs. Because of the multi-criteria nature of risk and expected value, risk management involves sacrificing revenue for risk. In this case, higher costs must be assumed to control the risk. This amount is a risk premium that must be paid. The graph presents the results of using G-SDDP with risk management. The range covered by the empirical solution is shorter. Given the edge asymmetry associated with risk, the solution's statistics change. Risk management involves increasing average costs of $387.0 to $392.84 in exchange for reducing the range from $178.72 to $151.94. G-SDDP, Generalized Stochastic Dual Dynamic Programming. Learning process. The G-SDDP MIP expansion case is presented using UBC cuts and inaccurate solutions. The graph presents cumulative time of solution versus scenarios. The graph shows the average time per scenario. The paper. A dynamical model of muscle, activation, fatigue and recovery. Presents the functioning of the muscles of the human body during exercise. The ordinate indicates the percentage proportion of each of the three groups of motor units to the total number of M0T motor units in the muscles. M8T motor units in activation, MFT fatigued motor units, and MUC-T engine units in the idle state. The timeline has been considered arbitrary to clearly show the details and main features of the curves. The graph shows the behavior of the average G-DDP time as a function of the effort made. As the effort increases, the average time decreases, as in the behavior of the human body. This demonstrates the learning capacity of G-DDP. G-SDDP and G-SDDP. Conclusions. In majority of cases, G-DDP algorithm converge to optimal solution. G-DDP speed up the solution of mathematical optimization problems with LP and MIP Benders Coordinators. G-DDP approach is faster than DDP. G-DDP-UBC is faster than standard benders. For the master problem, the integrated coordinator, IBC, is faster than the DDP coordinator. G-DDP-UBC detected the upper bound very rapidly but take time to prove its optimality. G-DDP-UBC plus inexact solutions may be faster than optimal solutions for MIP Benders Coordinators, and the relationship between the solution time and the dimensionality of the deterministic problem is linear, which implies that it is possible to manage very large problems in a short time. Very few understand that he is a professional expert in solving real-world problems using mathematical models. Alfred North Whitehead affirmed, "Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world." Thank you for your attention.